We say that capital F of z is an antiderivative of f of z if the derivative of this function, capital F of z, is equal to f of z. If D is some domain, and recall that a domain is an open set which is connected, then the function capital F of z is uniquely defined within a constant. This means that if we have two antiderivatives, that means that we have one function capital F1 and another function capital F2, whose derivatives are both f of z, then the difference between these two functions has to be constant. Let us prove this. Note that if we have some function g of z which derivative is 0 in the domain D, then this function g of z must be a constant. And the reason for this is exactly as in the real case. What we are using here is, in fact, that the domain D is connected. If the domain was not connected, then, for example, if it consisted of two connected regions which were separated from each other, then it's possible to have two constant values on these two sets and obtain that the function has derivative 0 all over. But in this case we have a domain, so this is not a problem for us. So we conclude that the function g of z must be a constant. This we are going to use in our argument, because when we are considering the difference between capital F1 and capital F2, this difference is equal to some function. Let's call it g of z. The derivative of this functions, the difference of this function is f1, the derivative of f1 minus the derivative of f2. Both of these are f of z, so this difference has to be 0. Therefore, this function must be a constant. So we conclude that f1 minus f2 of z is a constant. So this completes the proof. Here is another theorem. Let f of z be continuous in the domain D. Then the following statements are equivalent. Equivalent means that this statement implies this statement, and this statement implies this statement. So the two statements are the following. F of z has an antiderivative. The other statement is, given any point z1 and z2, then the integral taken over all possible contours, let's call them C, which lies in D, of the function f of z will be equal. So if we are integrating from this point z1 to z2, the integral taken over this contour is equal to the integral taken over this contour. So we have now two statements which are equivalent, and we also have a third statement which is the following. The integral over C of f of z dz, where C is any closed contour is 0. Okay, in the case when the integral is independent of the path between 2 points, then we can write this symbol instead of using the integral over C sign. And in this case we have that f of z has an antiderivative, so this integral is equal to the antiderivative f of z2 minus f of z1. Sorry for this misprint. And we write as we do in the real case, exactly as we do there. It's possible to prove this, and this is very useful in many situations. For example, if we want to integrate the function z square from 0 to 1 plus I, z square has an antiderivative, so the above theorem tells us that the integral must be independent of the path, so therefore we can this integral makes sense. This is the integral from 0 to the point 1 plus I on any path between these 2 points. So using the antiderivative of z square, which is 1/3 z to the power of 3, and inserting these limits, we easily obtain this number. Another example is the following. We are going from z1 to z2, and the integrand is 1 over z to the power of 2, z square actually. And we can find the antiderivative of this function as well, and which is using this formula for the antiderivative of a polynomial. We find that this integral can be written as the difference between z1 to the power of minus 1 minus z2 to the power of minus 1. So z1 and z2 should be different from 0, otherwise we get infinity here, and this is not good.